Let's imagine that we are in a manufacturing situation where we are producing thousands of parts each day. And it is known that 90% of these parts are of good quality and 10% are of a quality that would classify them as defective. We are going to randomly choose 2 for testing. And we're going to let X equal the number of good parts selected. So if we were to construct a probability distribution here, we would have our X value, our random variable, the number of good parts, and then the probability that X would take on each one of these values. Now, if we're going to choose 2, then there are 3 possible things that could happen. We could get 0 that are good. X is the number of good. We could get 1 that is good, or we could get 2 that are good. Now let's examine these probabilities. And let's do that using a tree. So with our first selection, we could get a good one or a defective one. And since we know that out of these thousands of parts, 90% are good, the probability that we would get a good one would be 0.9. And then the probability that we would get a defective one would be 0.1. Now that's the first selection. Now let's go on to the second selection. And just like any other tree diagram we have drawn, we're going to come off of each of the possibilities for the first draw and then draw the next set of branches for our second draw. Now the question then becomes, okay, in this second branch here, if I selected a good one on the first selection, does it change the probability that I draw a good one on the second selection? I am most likely not going to put the first one that I drew back. So the number in the selection process has changed. But if we think about the size of the group that we're selecting from, there are thousands of them. And if I take only 1, then that is some thousandth, depending on how many thousand we have here. And out to this many decimal places, 1 decimal place, or even 3 decimal places, depending on how many thousands, this probability is not going to change. So for all practical purposes then, since this probability is not changing out to any significant number of decimal places, then we can consider these events to be independent, since the conditional probability isn't changing. So here we go. We're going to fill this out then with the 0.9 and the 0.1, and I put a 0 on the end there, and that's fine. We can do that. 0.90, 0.10. So if we now examine this tree, we can see that there is one branch or one way to get 2 good parts. So there is one way to get 2 good parts, because there's only one branch out of this whole tree that contains 2 good parts. And so that probability then becomes the probability that I would get a good one times the probability that I would get a good one. Which really, I could write this in a bracket like this and make it a square. All right, now how many ways can I get 1 good one? Well, let's see. There would be 2 ways to get 1 good one. I could get a good one and a defective one, or a defective one and a good one. And what I realize is that with these 2 ways, I can really write this as 2 times the probability of a good one times the probability of a defective one. And that is because no matter which path I take, a good one and then a defective one, or a defective one and then a good one, it still comes out to 0.9 times 0.1. 0.1 times 0.9, same thing. So there's two of those, so I'll multiply that by 2. And then there's only one way to get 2 defective ones, and so that probability then becomes the probability that I would get a defective one, and then squared, because I'm going to multiply them together. So, thinking about that then, the probability that I would get 2 good ones, this top branch here, is going to be 0.81. 0.9 times 0.9. And then the probability that I would get 1 good one is going to be 0.18. And then the probability that I would get 2 defective ones is going to be 0.01. And so is this a valid probability distribution? Yes, because each of these is a valid probability. And then the sum of these probabilities is 1.